Hello, chemists. This is Miss Placino. I'm sorry I won't be in class today to kind of help you through this in person, but I'm optimistic that this screencast will help kind of get everything ironed out. So earlier for lab number 8, we got through everything in the pre-lab with the exception of questions E, F, G, and H. So I want to take a couple minutes now just to talk about what exactly you should do, since you're going to need to do these same things with your data. All right, so the first thing we need to do is plot a graph of the data. So we've got time, and we have volume of gas produced. So we have to figure out which one of these we should be putting on the x-axis and which one goes on the y-axis. Typically in a graph, your x-axis is your independent variable, and your y-axis is the dependent variable. So usually you pick the x-axis and then you monitor how the y-axis responds over time. Given that information, which of the two variables do you think should go on the x-axis? Hopefully you're thinking time and seconds. So I'm going to just jot that down here. Time and my unit. And that would leave volume of gas produced in milliliters to go on the y-axis. If you haven't done so already, take a minute or two, whatever it is, to go through and plot the data. I'm going to pause the video and get it plotted so you don't have to watch that semi-painful process. All right, so I've got all my dots plotted. Hopefully you have the same thing going on your sheet of paper right now. Needless to say, I can't just connect all these with a linear line. When you go to plot your data, you're just going to allow Excel or Google Sheets, whichever program you're using, to connect the dots. So I'm going to go ahead and just do that in a different color, hopefully to make it stand out a little bit. Again, you will not be plotting your data by hand when it comes to the concentration, temperature, and independent studies. You need to get your data in Excel or Google Sheets. All right, now that we've got the graph made, let's take a look at the other questions. Question F says, find the initial rate of the reaction. To do this, draw a tangent line at the beginning of the graph extending from the origin, then determine the slope of this tangent. Okay, so you're going to want something like a ruler or your ID card or like the back of a calculator so that you have a straight edge. We're going to start this tangent line. Hopefully mine turns out to be fairly straight, like it says from the origin. Put this in green. You're going to draw the tangent line for the initial rate. So, oops, sorry. I'm going to start it at the origin. Oops, it's not very straight. Make sure it's drawing. There we go. And I'm going to extend it through the first point. This is probably going to be a little bit easier for you to do on your spreadsheet plotted data, as that line's going to be a whole lot better drawn than the one that you just sketched by hand. Okay, we need to find the slope of this line. Hopefully you remember from some math class way back in the day that slope is equal to rise over run. So we have slope is equal to change in y over change in x. And essentially in this one, it looks like it's pretty close to like our first data point after 0, 0, that volume of 18 milliliters, and then the time of 5 seconds. This is the slope of the line, and this is the initial rate of the reaction. In 5 seconds, we produced 18 milliliters. If you'd like to go through and do the math, by all means, go right ahead. I think you end up with, I don't have a calculator on me, I think I remember it being like 3.6 milliliters a second. So that's the rate of formation of gas at the beginning of the reaction. Since we're looking for the initial rate, it's really important that you draw the slope, that tangent line from the origin. If you're drawing it at other places on the graph, it's not the initial rate. Question G, what would happen to the tangent line if the rate of the reaction decreased? All right, so if the rate gets slower, that means we're going to have fewer milliliters of gas produced each second. So we really should see that tangent line start to flatten out. It's pretty steep the way it's drawn right now, but as the reaction slows down, the line should flatten out. And again, that's just because less gas produced each second. And you can see over the course of the chemical reaction, the rate is steadily decreasing. And that's predicted by collision theory. I'll let you think about why. All right, last but not least, we need to find the rate constant, K, using the formula rate is equal to K times HCl, and those square brackets mean the concentration in terms of molarity. The reason this is the rate law for this equation is because we have a solid. In the example that we were using, it was magnesium, and our other reactant, hydrochloric acid, is aqueous. We can change the concentration of a aqueous solution in a gas, but we cannot change the concentration of a pure solid or liquid. So the rate is really only dependent upon the concentration of HCl. So I've got my rate, which we've calculated to be 3.6 milliliters per second, is equal to K, some constant. That's what we're trying to solve for. And if you look back on the previous page, you'd see that the concentration of HCl was 1 molar. And I'm going to write it as 1 mole per liter instead of just capital M. Now, hopefully you look at this and the math seems really, really straightforward. 3.6 divided by 1 is, of course, 3.6. K is confusing because the units get weird, really for a lack of a better way to describe it. We know from math class 3.6 milliliters over second. We're going to divide by the molarity. It's just like multiplying by the inverse of the molarity. I'm going to leave the number out of there because multiplying or dividing by 1 isn't going to change the value, but that gives me liters over moles. So I'm going to get an extremely strange looking unit. If you want to make it a little bit cleaner, well, actually, let's just cut to the chase first. We'll clean it up later. So I have 3.6 milliliters times liters over seconds times mole. I know that that is a bizarre and really for the most part meaningless unit. The units for K really just kind of serve to cancel everything out. You can make this a little bit cleaner by getting the volume units to agree. So for example, I can get both of my units in terms of liters. I know that there are 1,000 milliliters in a liter, so I could represent this as 0.0036 liters per second. Again, multiply by 1 liter over 1 mole, and I end up with 0.0036 liters squared per second mole. I know that is not much clearer as far as what those units mean. Again, they're really just there to get everything to cancel out, the unwanted units. In this case, one of the volumes, the liters and the seconds, to give us something in terms, the liters and the moles to give us something in terms of volume per second in the rate. And that's really it as far as the calculations go. Really quickly, a couple other things just to make sure we're on the same page. As far as what I'd like to see on your graphs, let's pull up, where did I put it? Oh, wrong one. This. Okay, so when you think about it, we did 3 different studies: a concentration study, a temperature study, and an independent study. For the concentration study, you should have 3 different molarities. So you should have 3 different lines on this graph. 1, let's do them in different colors, 2, 3. So just make sure that you are drawing the tangent line. Should zoom in on that a little. Or not. Oh, there we go. And I'd like you to calculate rate and K for each concentration. If you make your graphs a reasonable size, you can probably do your calculation just directly next to them. For the temperature study, you should have 2 different graphs plotted. They should all take on this shape ideally. For this one, just draw the tangent line. And finally, we have your independent study. Please be more specific than just saying independent study. Tell me which variable that you studied. You didn't study independence, you studied something else. And you should have minimally 2 different volumes to look at. Again, give me the tangent line. You don't have to go through and calculate the rate in K. I'm sure you'll get pretty sick of that. Is there anything else I wanted to talk about here? Include for each of them a key, or go through and label which is the different concentration, which are the different temperatures. And remember, if you're printing out in black and white, there's a really good chance that I'm not going to be able to differentiate between 3 different shades of gray. So in Excel or Google Sheets, maybe change the line type so that it's a little bit easier for me to see which is which. Okay, and last but not least, I just kind of want to update what is on the rubric. So, what's that? Back to this. So hopefully no surprises and definitely no changes on the data and theoretical calculations. The results, kind of what I just talked about as far as what should be shown on the graph. There are also some calculations that I'd like you to include. First off, find the limiting reactant. You're working with the calcium carbonate and hydrochloric acid. You should be able to figure out which one's going to run out first. Based on that information, you can predict volume of CO2 formed. In other words, the theoretical yield. Sorry, that did not work out right. Theoretical yield. You can calculate a percent yield. So really the calculations that we just went through, or I guess not just went through, but we went over in the pre-lab when we got to do that in person. Number 4, you can calculate rates for a concentration study. And please calculate all 3 rates for the concentration study. And you can calculate K values for concentration study. And again, these 2, if you've got things set up in a pretty reasonable way on your graph, you can probably just do the calculations right next to them. If you'd prefer to do it on the blue and yellow data sheets, knock yourself out. Let's see. Make sure that when you are turning in your graphs that you have 1 per person, or 1 set of 3 to be more specific per person. They're going to be identical, hopefully for you and your lab partner. So if you're working on Excel or Google Sheets, split up the work. Maybe, 1 person does a concentration study, the other person gets stuck with 1 or 2 of the other ones. You don't have to kind of recreate the wheel. You can work with your lab partner, but you should turn in your own sheet of paper. Finally, on Thursday, we'll go ahead and do the qualitative quiz, and on Friday, we'll do the quantitative quiz. Okay, I hope this was helpful. I'm sorry again that I am not here to do this in person. If you've got questions, hopefully we'll have some time to tackle them after the qual quiz on Thursday.